Biot-Savart law is used to calculate the magnetic field due to current carrying wires when you're a distance r away. If you have a current carrying wire, you can define a little piece of the wire of length ds that points the same way as the current. That piece of wire is the distance r away from the spot where you want to know the field. Since there's a cross product in the relationship here, we can use the right-hand rule to figure out the direction of that field. Point your fingers in the direction of the first vector, ds. Curl them in the direction of r hat, a unit vector pointing up to the point. Thumb is perpendicular and gives you the direction of dB. So my thumb points out, so dB points out as I've shown here. But because we have an earlier right-hand rule that's a little easier to use, we can find the direction another way. Just point your thumb in the direction of the current, grab the wire, fields circle wires, so the field must poke out at the top. So because that's the case, we don't need to use the vector version of the equation because we can find the direction really easily. Instead, we can use the magnitude of this equation. So to find the magnitude of a cross product, you do the length of one, so the length of ds is ds, the length of a unit vector is 1, and then the sine of the angle between them. So this is the equation you can use to find the magnetic field due to a little piece of current when you're a distance r away. So let's apply that to this problem here, an infinitely long wire where we want to know the field a distance d away. This is done in the PowerPoint, but there's some steps that were skipped. So let's do it again. So first, the direction of the field at this point is poking out from the direction of current, circular field. So we know that the magnetic field is out here at the top, so at least we get the direction right. To use our equation to calculate the size of the field, we're going to need to define a coordinate system. So I'm going to call this my y-axis here, and this my x-axis. Here's my origin. I'm going to pick a piece of the wire of length ds, except I'm on the x-axis, so let's call it dx. So dx is the width of that little piece. It points the same way as the current. I can define r then as this distance here from my piece of current up to the point where I want to know the field. And r hat would then be a unit vector that points that way. So then the angle theta, which is the angle between dx and r hat, is this angle here in this picture. I can also locate the piece of current that I picked. I picked this piece here. I could have picked any other piece on the wire. I need to locate that measured from the origin with a new variable, which I'm calling x. So x is the distance from the origin out to where you picked your little piece of the wire. Okay, notice we can, our equation has a sine theta and an r squared in it, so we need to substitute for these quantities. You should see that r, because we have a right triangle here, is d squared plus x squared to the 1/2 power. Right? From Pythagorean's theorem, d squared plus x squared equals r squared. Okay, we can also say that the sine of theta is the same thing as the sine of 180 minus theta. Okay, that's a property of sine. And then the sine of 180 minus theta is opposite over hypotenuse, d over r. Okay? So I can now substitute those into my equation for dB. So dB is that constant mu naught I over 4 pi. I'm writing this equation down. I have a dx instead of a ds. And now I got to substitute for sine theta. Sine theta is d over little r, but there's a little r squared on the bottom, so that's d over r cubed. And now I can rewrite it substituting for r here. I could pull the d out with the other constants, the big D. And I have a dx on the top and an r cubed on the bottom. But r cubed is this quantity cubed. So that's d plus x, d squared plus x squared to the 3/2 power. So this is the equation for the magnetic field just due to this little tiny piece. Of course, the wire is made up of a whole bunch of little pieces, each with the field given by this equation. So if you want to calculate the overall field, you have to add the dBs due to every little piece of charge on this infinitely long wire. In other words, we need to integrate. So we can say that B, which is the integral of dB, the sum of all the dBs, is, if we pull out the constants, mu naught I d over 4 pi, integral of dx over d squared plus x squared to the 3/2 power. I need to put my limits of integration on. I'm integrating with respect to x. So you can see I have an infinitely long wire, so x is going to go from minus infinity to plus infinity. Okay, this is an integral that is solvable. It's solved in the PowerPoint. If you just look there or use Wolfram Alpha or remember your calculus, you can do this integral. I'll just state the result. The result is mu naught I over 2 pi big D. That's the equation given in the PowerPoint for the field of an infinitely long wire carrying current I when you're a distance d apart. We will use this equation a lot, and notice that sometimes the book or the PowerPoint will write it a little differently. They'll put a 2 on the top and a 4 pi on the bottom. It's the same equation. The reason they write it that way is this constant mu naught is usually written as 4 pi 10 to the minus 7. So by having 4 pi over 4 pi, the 4 pi's cancel and you just have a 10 to the minus 7. I personally think that's not worth doing. So this is the equation I usually remember as the field for a long straight wire. Now of course infinitely long wires do not exist, but we can often have a wire that's pretty long. And as long as you're really close to the wire, it looks infinitely long. So this is a good approximation for the field near relatively long straight wires.